Hello everyone, my name is Ruyu Wang, and the presentation today is about improving the effectiveness of deep generative data. Let's have a look at the background of this work. What's the question here? Recently, I think everyone has noticed the new breakthrough on generative models, which enables people to access high-quality synthetic data in many ways. However, here we are curious about one thing. That is, how good are the synthetic data from deep generative models when serving as training data? This can further be divided into two cases. One is using synthetic data only, where we replace real data completely with synthetic data. And the other case is using synthetic data as data augmentation. However, in both cases, researchers often observe a problem. That is, when testing on real data, a performance gap exists between models trained on synthetic data and models trained on real data. This means that synthetic data is less effective than the same amount of real data. Also, the performance gain brought by synthetic data saturates quickly, meaning the improvement is hardly seen over a certain amount of data. Moreover, the positive impact of synthetic data diminishes as more real data is available. Why? What's wrong with the synthetic data? In literature, this problem is generally described as domain gap. But this is not enough. We would like to dig more into the factors causing this gap. In this paper, we defined a new taxonomy to classify the factor into three types. First, the appearance gap. This describes the gap induced by artifacts like unrealistic textures, which is more often observed in the synthetic data acquired from simulators like CAD. Second, the content gap. It addresses the distribution mismatch between synthetic and real data, and not only from the class level, but also from the attribute level. Third, the quality gap. It describes the distortion in the generated images, like the fish with two heads. In the following slides, I will present some empirical investigations to show that the content gap is the primary issue among these three factors. For the empirical investigations, we focus on the image classification task on Cypher10 dataset. And note that beside the real Cypher10 dataset, we also have two synthetic Cypher10 datasets generated by two popular generative models. So, the first sign we observe is that the performance gap between synthetic and real data is not mutual. Let's have a look at this table. Here we have three classifiers trained on different sources of data and test on real data. You can see significant gaps when training on synthetic data and then test on real data. But the other way around, when training a classifier on real and using it to classify the synthetic data, there is almost no gap. The real classifier can classify synthetic data with no problem. How does this sign link to our three factors? First of all, we rule out the appearance gap because the deep generative models are explicitly optimized against this. Second, we rule out the quality gap too, because if the quality gap is a problem here, it will hinder the performance of the real classifier too. So this leaves us the content gap here. Let's continue with sign 2. Here, by observing the training curves of the classifiers, we notice one thing. That is, the training accuracy of the synthetic classifier saturates way quicker than the real one. They spike over 80% accuracy within the first 20 epochs. This feels like the classifier trained on synthetic images are solving an easier task. But this is not true, because they are solving the same 10-class classification task. This links us back to the content gap among all gaps, where we now hypothesize that the synthetic data from deep generative models forms a simplified dataset where rare samples are missing. We further show the third sign to support our simplified dataset hypothesis. In this experiment, we check for the loss brought by each synthetic samples. Why? Because if a synthetic sample contains novel information, it should stimulate a high loss to update the model. However, as shown in the solid bars here, the synthetic samples mostly have a very small loss when being checked by a real classifier. Note that the y-axis is in log scale. We also plot the losses from the real data when being checked by synthetic classifiers in dotted bar here to emphasize our point. This means most of the information the synthetic data can provide is already learned by the real classifier. Up to this point, it is clear that the content gap accounts for a large portion of the performance drop in downstream tasks. Moreover, a feature extractor trained on such a simplified dataset may learn biased representations. So, to alleviate the content gap, we propose two strategies, pre-train and real guidance, to regularize the downstream networks. Our pre-train guidance uses a model pre-trained on large-scale datasets like ImageNet to guide the training of the current model. Specifically, we encourage its feature extractor to maintain a data span similar to that of the pre-trained model. In this way, we prevent the models trained on a synthetic dataset from converging into having less distinctive representations. Also, our design allows the current model to use a different network than the pre-trained model, which is useful because not all networks have available pre-trained weights. As for the real guidance, we tackle the case where a few real samples are available to guide the gradient flow of synthetic samples. Considering the gradients from real data as positive influences on the model, we project all the gradients from synthetic data to be at most perpendicular to the real data. In this way, we prevent the synthetic data from overfitting itself and narrowing the content gap by introducing information from the real data. Finally, we present the experiment result of our proposed method. We conducted all experiments with ResNet 50 classifiers. Please find the details in the paper. We consider two sets of experiments, zero-shot and low-shot. By zero-shot, it means using only the synthetic data for training. Here we can see in the table, across 4 datasets, our pre-trained guidance provides better performance in most cases. Specifically, when using ImageNet initialization is not beneficial, like the SDIC dataset here, our method shows its advantage over other methods. In this slide, we present the low-shot scenario, which means some real samples are used during the training. In this scenario, we compare our method to data augmentation and adaptation baselines. As shown in the table, the baseline data augmentation already performs much better than data adaptation methods like DADA. Moreover, applying our method to the data augmentation baselines significantly improved the classifier performance in most cases. This successfully demonstrates the effectiveness of our method. In conclusion, we believe that the content gap is the main factor causing the performance drop for the synthetic data from deep generative models. However, this does not mean using synthetic data is a no-go. In this paper, we propose a regularization method to mitigate the performance drop caused by the content gap and achieve up to 23% improvement on multiple datasets. Thank you for listening.